Okay, this will be a hopefully pretty quick video, kind of going over, a practice question and one of the concepts we get between calculating tension, seeing objects that are hanging, or an object is sitting on a rope and the rope has to have tension on both sides. And the principle behind all of these kinds of questions, and so, sorry, let me just show you an example of another one. So I've drawn one, a sign hanging from a roof and a wall beside it. There's also, like, if you have like a wire and an object sits on the wire and pushes the wire down, the wire looks like this with the object in the middle, and you might have to calculate the tension here and here. Currently in the one I've drawn, you're calculating the tension here and here. You could have a pulley like this. You might have to calculate tension here. And if things aren't moving, which is the case with these questions, they will move in future lessons, but here they're not moving yet. When objects are not moving, they have a net force of 0, which means the addition of every single force, accounting for the directions the forces are pointed, the addition of all of the forces should equal 0, because one thing we know is if F net, the addition of all forces, equals 0, the object is either accelerating or not moving at all. And of course, in the case of the sign, we would consider it was the first one. It's not, or the second one, whichever one I said, it's not moving at all. So what we do is we can do something similar to before when we're adding vectors. We could say, let's say if a person was, here's a river, person swims across the river, and the river pushes them downstream, we can kind of figure out a resultant. So even though we're not using arrows in the same direction, so for projectile motion, I always said, always do x calculations, always do y calculations. Well, we could add our vectors, including their direction. So one vector could be this, another vector could be that, for the resultant vector of this one, right? It doesn't really matter what the directions are because the arrows have the angles attached to them. Of course, the question should tell you what angle is appropriate. And then when you have that, you can figure out basically the sine and cosine laws, or basically make it so that you can find any of the sides and it already accounts for the different directions, whereas our regular formulas do not account for our directions. So we can do this, and we can draw vector diagrams to basically tell us what's going to happen. And so really what happens is we expect the overall movement of these vectors when we add them together to equal 0. So much like if I said, I'm going to walk 10 meters this way, I'm going to walk 2 meters this way, I'm going to walk 8 meters this way, 8 meters this way, 2 meters this way. You see what I'm doing, and then we get back to here. This would be another 2 meters down and 6 meters across. Of course, this is not drawn to scale. Look at that. We just did a whole bunch of things, but we ended up where we started, which basically means our displacement in this example is 0. Displacement is 0. It's as if we didn't move at all. This kind of vector addition is exactly what we're going to do here. So I'm going to get right into it. So here's a practice question I have on the board. Calculate tension on the ropes. I know it's very simple. I've included all of the pertinent information. If I forgot something, we will catch it as we go. So what we want to consider is, okay, I'm going to draw a free body diagram, and I'm going to draw it on the side just so I don't mess up my drawing and make it hard for you to see what's going on. I've got an object that's hanging. There's a force of gravity pulling it down. That's why it's hanging. There's a force of tension on this rope, force of tension 1, I'm going to call it. And then horizontally, there's a force of tension 2 on this rope. Notice that these ones are perpendicular to each other because force of gravity is straight down. And as best as I could draw it, force tension 2 is horizontal. And so this is our free body diagram. And we say, okay, all of these forces are acting on this at the same time, but the sign is not moving. And that means all of these forces must add up to 0. And we can add these like normal vectors. Same way as if I said I ran this way a certain number of meters, this way a certain number of meters, and this way a certain number of meters, that would equal a net displacement of 0. And so it's the exact same thing we're going to do with forces. So we would say, okay, I'm going to, and it literally does not matter which one you start with, I'm going to start with force of tension 2, and we add tip to tail. I'm going to add force of tension 1 to it, and then I'm going to add force of gravity to it. So this was the force of gravity. Notice this arrow is that. Force of tension 1 That arrow is this. There should be all the same. Force of tension 2 is this one. Now, it gets tricky when you're trying to draw your triangle because this one is a right angle triangle because this one, the force of tension 2, is to the left perfectly and force of gravity is down. So that is in fact a 90-degree angle. Sometimes it does not work out that way. So make sure to be careful when you're building your triangles. The question will have given you angles for some of the forces, and so that will help. But we have now drawn a diagram, a vector addition diagram to say all of the forces on this object point back to exactly the beginning, meaning there is no net force. Remember, when F net equals 0, there is no movement. This is what must be the case for questions like this. And so, essentially, we can start doing our math to figure out how much tension is on each of these strings. And so we know, okay, force of gravity down equals mg equals 30 times 9.81. Let me calculate that real quick. 30 times 9.81 is 294.3. Whoops. 294.3. That is this side of our triangle. And we say, okay, hold on. Is there anything else I can figure out? Currently, I didn't give either of the other sides. We have one angle, but that doesn't tell us anything about the other two angles. But we have this angle shown here, which is 60 degrees. And that's a 60 degree from this line, from this force of tension 1 to the horizontal. I know my box isn't flat. It's supposed to be flat. And so that is, this angle is 60 degrees. And so now what we can do is say, okay, well, based on having any two pieces of information other than the 90-degree angle, of course, we can do cosine, sine, and tan, whatever we need to figure out these pieces of information. And so we can continue as follows. So if we wanted to figure out force of tension 2, we know that that would be a tangent function. And so tan 60, whoops, equals opposite over adjacent. So 294.3 over force of tension 2, multiply that up, divide that down, and so we get 294.3 divided by tan 60. And so force of tension 2 now equals 169.9 newtons. Perfect. And then we can do the exact same thing to figure out force of tension 1, which of course is going to use the sine, or you could use cosine with the one you calculated, or you could use Pythagorean theorem because we now have two sides. I'm going to use sine because I want to keep this exact value because this one I rounded just for the sake of writing it down here. But I'm going to use sine because this value is not rounded. That's the exact value I got. So sine 60 equals opposite 294.3 divided by force tension 1. And of course, that's going to be 294.3 divided by sine 60. 294.3 divided by sine 60. And we get force tension 1 equals 339.8 newtons. Again, I've rounded this number. But what you can see here is, in quick summary, so we basically finished the question. We said since this object is not moving, the net force must be 0. And so once we drew over here our free body diagram, we said, okay, here are all the forces acting on this object. All of the vector arrows must add up to 0, meaning the place that the first vector started with is where the last vector ends. And that's how you know F net is 0. If it had gone like this and ended here, that would mean your net force actually is down like that. That would be the resultant, and you would move. So, of course, any of these questions were not moving, so we don't do it like that. So we added them up tip to tail, all three of them. In this case, there could be 4 or 5 or 20 or whatever. We add them up tip to tail, and they end on the same spot we started with, which means no net force, which is exactly what we need to do this question. And then you can use whatever pieces of information you're given. Since we had mass, we could find force of gravity. And since we had this angle, we could figure out the other two sides. Again, this happened to be a right angle triangle, but if I was to redraw it, let's say, and give you perhaps this and say that this is a 30-degree angle, well, all of a sudden now we have to redraw our triangle, and I'm going to start with this one again. So that would be 60 degree for this one. I'm going to draw force of gravity. I'm going to draw this one next, which would be at a 30-degree angle to the horizontal, right? So that's like a 30 degree there, something like that. And then force of gravity will go down. And so the question is, we don't know if our triangle is a right angle. Well, it actually already you can tell it's probably not a right angle. So you can use sine or cosine law to figure out the rest.